Hey everyone, I'm back. This is our last installment. Thank goodness, right? Our last installment of quantum theory uh, and electron configuration and notation. So today's lesson is going to expand on our electron configuration and go into how to write more in that electron notation, which will actually include a representation of all four of the quantum numbers that we've already talked about in previous lessons. So let's take a look at the electron configuration rules and electron notation and how we write those and some of the rules that go into writing that electron notation. So hopefully you have your notes for these. We have a bit more than our last short little lesson that we had. So let's take a look here. Electron notation. So electron notation gives us a visual representation of the four quantum numbers. And if you remember our four quantum numbers, okay, those are orbital notations. So where we can find those electrons using probability and how much energy those electrons have around the atom. So our first, just a little review here, our first quantum number is the principal quantum number. Okay, and if you remember, that represents the energy levels. So those can be represented by the numbers 1 through 7 to tell us about the amount of energy in that principal quantum number. Our second one is the orbital quantum number. Okay, using probability tells us the shape where that electron will be found. Okay, that sublevel shape, S, P, D, and F, as we've mentioned before. Our third quantum number is the magnetic quantum number. And we haven't talked as much about this, but remember, these orbitals can have different shapes. Well, the shapes can lie on different axes and things like that. So that magnetic quantum number represents one of the different positions on an axis that orbital can lay. And then, of course, our last quantum number is the spin quantum number, just telling us the direction of the electron spin, either clockwise or counterclockwise. So let's take a look at how we write an electron notation. I'm going to give you a couple different representations for how you can write this. There is a more traditional method, but there's two methods that I will allow in our classwork. So first thing that we'll look at is we're going to use we will use circles to represent each orbital. Okay, slashes within those circles will represent the electrons. Okay, so if we take a look here, I have some circles for S and P orbitals. If we remember, as we were going through the material on the different quantum numbers, okay, there's a number of different positions that each of these can have. So S has one circle, P has 3 circles. How many do you think D has? Okay, so how many electrons can be in a D orbital? Okay, we've looked at this in our previous lesson. Okay, slashes represent the electrons. So in this particular orbital, there are 2 slashes to represent the 2 electrons. So if I had an S orbital, okay, an S orbital can hold a maximum of 2 electrons. So I'll put the 2 slashes in there to represent those 2 electrons. If you remember, a P orbital can hold a maximum of 6 electrons. So what I have represented here by the 3 circles, each of those circles can hold 2 electrons. Also, each of those circles represents the position relative to the x-axis for that magnetic quantum number. So most notations are actually done using boxes with arrows instead of the circles and slashes. Why are we doing it differently? It's just a little bit easier, a little bit quicker, okay? but most methods are done with boxes and arrows, something kind of like that. Okay. I've always done it with just a line and then the two arrows for each of those orbitals. So there's a few rules when we are filling those orbitals with the arrows or the electrons. Okay, there's a few rules that we have to follow. We can't just put the arrows and electrons wherever we would like to put them. Okay, there's rules regarding where we can actually put those. So the first rule we're going to look at is called the off-bow principle. Okay, the off-bow principle says that electrons fill the orbitals of the lowest energy first. Okay, those electrons want to hold the least amount of energy possible, so they're going to fill the orbitals that are lowest energy first. Okay, and it'll fill up from the bottom, okay, that lower energy level before moving to fill the next higher energy level. And if you remember, as we were writing our electron configuration, okay, 1s2, 2s2, 2p6, as you write that electron notation, you continue to increase in energy. So you would fill the 1s orbital with electrons before you fill the 2s orbital with electrons. I'll show you how this works. So s orbital, then p, then d, then f. Our next rule that we'll take a look at is called the Pauli exclusion principle. Okay, and the Pauli exclusion principle says that each orbital can only have 2 electrons. Okay, it can't hold 3 electrons or more. Okay, it can only hold 2. So all other electrons are excluded from being occupied in that orbital. Okay, 2 electrons in each position. Okay, but the other part of the Pauli exclusion principle says that each of the electrons, those 2 electrons that can be held in that orbital, have spin in opposite directions. So one of those electrons is spinning clockwise and the other is spinning counterclockwise. So if you remember looking at that box version of the electron notation, the more traditional method, the arrows are pointed in opposite directions. Our last rule that we'll look at is called Hund's rule. Okay, and Hund's rule says that there is no pairing of electrons in P, D, or F sublevel orbital positions until each of those orbitals, is given at least 1 electron. Okay, so each orbital for the P, D, or F sublevel will get 1 electron before any of them get 2 electrons. Meaning, I'll fill 1 electron, the second electron then goes in the next orbital. I can't add it to that first orbital due to Hund's rule. Okay, I cannot have a pair unless each of these orbitals has one first. So the third electron would be represented by another slash in the third orbital. Okay, I have 3 circles here, so what type of orbital quantum number, what shape are we talking about here? Okay, p orbital, right? So 3 positions, it can hold a maximum of 6 electrons. So there's our first 3, okay? And again, no pairing of electrons. So how do we make our electron notations? Again, we're going to use circles to represent each of the electron positions, okay? That magnetic quantum number for each of those circles. So hydrogen, okay, if we write out the electron configuration for hydrogen, we already know that's 1s1. Okay, it has 1 electron. Okay, helium, 1s2. Okay, all in 1 orbital position. Okay, the 1s orbital, and a total of 2 electrons. So if I were to write these, so hydrogen, 1 slash, 1 electron, that is it, we are done. Okay, helium has 2 electrons, so I'll have 1 circle to represent the orbital, and then 2 electrons. Okay, so I'll make 2 slashes for the electrons. If you want to do the box method with the arrows, you absolutely may for this as well. Okay, so carbon, okay, this is how I want us to write these out. So first you will write out the electron configuration for carbon. Okay, carbon has 6 electrons, so first it will fill the 1s orbital, which has 2 electrons. then the 2s orbital, which has 2 electrons, and then we get to the 2p orbital, and with a total of 6 electrons, we'll only have 2 electrons in the 2p orbital. So here's how we will write this out. So we have a circle for our 1s orbital. Okay, holds a maximum of 2 electrons. We don't need any additional circles there. 1 electron, 2 electrons in the 1s orbital. We move on to the 2s orbital. Okay, 1, 2 electrons. And then we have our 2p orbital. Okay, so this is a little bit off-centered, but usually we'll draw these circles or boxes underneath those as we write out the electron configuration and electron notation. So 2 electrons, again, due to Hund's rule, we cannot draw the second slash in with the first slash, so it goes to the next orbital position. And that would complete our electron notation for carbon. Let's take a look at fluorine. Okay, fluorine, same thing. So 1s2, 2s2, 2p5, 5 electrons in the 2p orbital. So our first 1s orbital has 2 electrons, so we have 2 slashes, opposite directions. Our 2s orbital also has 2 electrons, so 2 slashes in opposite directions. And then our 2p orbital, okay, again has 3 positions. Okay, if you remember from our first lecture, okay, it has 3 positions. That's why there's the 3 circles, okay, or 3 boxes if you choose to do boxes. Okay, and we still have to follow those rules. Okay, so the first 3 electrons, each of those positions will get 1 electron before we compare any of them up. Okay, and then our 4th and our 5th electrons would get paired there. Okay. All right, so last thing, okay, to wrap this up, where are the quantum numbers? Okay, we have the electron configuration, we have the electron notation here. Well, we have 4 quantum numbers. Where are they located? How is this a visual representation? So where is that principal quantum number located? Right, it's that very first number, the 1 or 2 or 3, either 1 through 7, okay, for our principal quantum number, okay, for each of those orbitals. So we have 3 of them represented here, okay, which tells us about how much energy those electrons have. Okay, our second one, our orbital quantum number, okay, that's the shape, right, orbital quantum number, so S and P in this example of carbon. And then our magnetic quantum number are those 3 positions, okay, how they align compared to the x-axis. So there's our 3 positions for the 2p orbital. And then, of course, our spin quantum number is represented from the slashes, okay? So hopefully this helps you guys with understanding how to write out our electron configuration with the electron notation. Again, this is our last bit on quantum numbers and quantum theory for atomic structure. I look forward to moving on to the next little bit here in our unit on atomic structure here as we move on. So let me know if you have any questions. Thanks a lot.